Welcome back. You left with 3 exercises. 2 of them contain traps that matter today. Exercise 1. Unroll the stream across 3 layers. The tempting answer applies every layer's function to the original vector. Wrong. And the wrongness is the point. Each layer reads the stream as it is when it arrives there. Layer L+1 reads via L+1, which already contains layer L's right. So delta is a sum of 3 terms, each evaluated at a different progressively updated vector. And if you're now thinking, hold on, if delta is that nested nonlinear mess, isn't linear transport dead before we start? Why would anyone expect a straight line relationship to survive 10 layers of attention and gating? Then you've asked exactly the right question. Here's the physical picture that keeps the hypothesis alive. Maybe a feature gets written once, early, by nonlinear machinery, and then the later layers simply don't touch it. It just sits in the stream, carried along, while they work on other things. If that's the life story of a feature, then along that feature's direction, the stream behaves like a wire, and wires are linear. Whether that story is true is an empirical question. That's why we build a test instead of an assumption. Exercise 2. Quick arithmetic. The Python ruler on the stream 7.1 reads 4.2 plus 0.8, 5. Solidly Python. Exercise 3 asked you to design your own transport test. Keep it in front of you. Today we take the 3 designs almost everyone invents first. And we don't wave at their flaws. We prove each one wrong with a counterexample you can verify by hand. If your design survives all 3, you have essentially reinvented the paper. First, what raw material does any test have to work with? This. Run the model over a pile of ordinary text. At every token, the stream passes layer L. Record that vector. It later passes layer L plus K. Record that too. Each token gives you 1 pair. Upstream vector, downstream vector. Collect a few 100,000 pairs. That table of pairs is the entire dataset. Every test we discuss today is some computation on this table. Now the claim, stated like a contract. There exists a single matrix T and a single shift vector B, fitted by US from that table, not stored anywhere in the model, such that for every token, the downstream reading of feature F is approximately the ruler dF applied to T times the upstream vector plus B. 1 T per pair of layers, and the same T must work for all 16,000 features at once. That's what makes this a claim about the stream, not about one lucky feature. Why allow the shift B? Because some directions carry a constant baseline. It's the intercept of a line, and it costs almost nothing. One rewrite makes everything that follows feel inevitable. The ruler applied to T times V is just some fixed vector, T transpose D, dotted with V. So the contract really says the downstream reading is an affine function of the entire upstream vector, some combination of all 2,300 coordinates, plus a constant. Remember that phrasing, of the entire vector. It is about to demolish test number 1. And to be clear about what the contract does not say, it does not say delta is 0. 10 layers did plenty. It only says that through this one keyhole, one direction's shadow, their combined effect looks like a straight line. How well must the approximation hold to count as transported? For now, hold the intuition. Perfect prediction means transported. No better than guessing the average means synthesized. We'll turn that dial into a precise number in a few minutes, and video 4 is entirely about where the dial can reach. Now, test number 1. Test 1 is the design nearly everyone writes first, and it sounds completely reasonable. The feature is a direction. So take the downstream ruler, the layer 10 dictionary's direction, the only definition of the feature we have, and apply that one same ruler in both places, to the upstream vector and to the downstream vector. 2 numbers per token. Compute their correlation across the table. High, transported, low synthesized. Before I touch it, pause here. Can you build a world where transport is perfect? Exactly linear, nothing lost, and yet this correlation is exactly zero. Two dimensions suffice. Suppose the layers between L and L plus K do exactly one thing: rotate the plane by 90 degrees. First, is a rotation even allowed? Video 1 said layers only ADD. Yes, to turn V into A times V, the layers just have to add the difference. A minus identity times V. Delta equals A minus I times V. Additive updates can implement any linear map. So, rotation by 90 degrees, perfect linear transport, a fixed matrix, invertible, nothing lost. Put independent activity in the two coordinates, x1 and x2, and let the feature ruler be the first axis. Upstream, the ruler reads x1. Downstream, the rotation has moved the second coordinate into the first slot. With a sign flip, the ruler reads minus x2, and the correlation between x1 and minus x2, two independent quantities, is zero. Exactly zero. Perfect transport, the test reads nothing. Why did it feel so safe? Because the test silently assumes the transport never mixes directions, that whatever lives on axis 1 stays on axis 1. Write a diagonal matrix, shrink axis 1 a bit, axis 2 a bit, no mixing, and the naive test works flawlessly. The hidden assumption is the diagonal case. But mixing directions is what matrices do. It's the generic case, not the exception. And remember the deeper reason from video 1. The dictionary at layer 10 belongs to layer 10. Upstream, nobody promised the ruler DF points at anything meaningful. The only honest question is whether some combination of all upstream coordinates predicts the downstream reading, which is exactly the affine contract from a minute ago. Constraint 1, earn the hard way, consume the entire vector. Test 2 comes from the causal school. Forget correlations, intervene, reach into the model, delete the upstream signal, and watch the downstream feature. If it dies, it depended on upstream. Surely that's transport settled. To examine this cleanly, let's shrink the cast to two characters. Z is the upstream quantity, what one particular direction of the upstream stream carries. And Y is the downstream feature reading, our usual DF measurement at layer L plus K. Ablating means set Z to 0 in the stream and let the layers recompute everything downstream. One question, pause here. Can you build two worlds, one where Y is linearly transported from Z, one where Y is manufactured from Z nonlinearly, such that this experiment returns the identical verdict in both? World 1. Y is a plane copy, a constant C times Z, linear as it gets. World 2. Y equals Z squared, genuinely manufactured by nonlinear machinery. Now run the experiment in both worlds. Set Z to 0. World 1. Y drops to 0. World 2. Z squared also drops to 0. Both features die completely. The interventionist reports full causal dependence in both worlds. Identical verdicts from opposite mechanisms. To say precisely what ablation missed, we need the series favorite score, so let's define it once carefully. R squared measures how much better is your prediction than just guessing the average. Take your prediction errors, square them, average them, divide by the variance the error you'd make guessing the mean every time, subtract from 1. Perfect prediction, error 0, R squared 1. Prediction no better than the mean, ratio 1, R squared 0. It can even go negative if you predict worse than the mean. That's it. Now, what's the best linear prediction of Y from Z in world 2? A line, slope A, intercept B. The calculus of least squares, you'll derive it yourself tonight. Homework 1 says the best slope is the covariance of z and y divided by the variance of z. Take z symmetric around 0, so its mean is 0. Then the covariance is the average of z times z squared, the average of z cubed. And for symmetric z, every positive z contributes z cubed. Its mirror image contributes minus z cubed. They cancel in pairs. Average of z cubed, 0. Slope 0. The best line through the parabola is flat. It predicts the constant average and nothing more. R squared, exactly 0. The scorecard. World 1, ablation says fully dependent. R squared says 1. World 2, ablation says fully dependent. R squared says 0. Regression tells the worlds apart. Ablation cannot. Then why not throw ablation away? Because regression has its own blind spot, the oldest one in statistics, correlation without causation. A high R squared says the downstream reading is predictable from upstream. It cannot say the model actually uses that channel. Maybe both are driven by something else entirely. Ablation certifies the dependence is real. Break the channel, the feature breaks. So the tools answer different questions. Regression for the form, ablation for the reality, and the paper will need both. Constraint 2. One honest aside. I chose Z symmetric to keep the algebra clean. Real activations coming out of ReLUs are not symmetric. It doesn't matter. One pair of worlds that fools ablation is enough to prove ablation alone can't settle transport. Enter the pragmatist. You want the whole vector, you want regression. Fine. Take the table of pairs and fit the matrix T by least squares. Make T times upstream, match downstream, entry by entry. To see what could go wrong, calibrate on an extreme case first. Focus on predicting one downstream coordinate. That uses one row of T, 2,304 unknown numbers. Suppose, just for calibration, you had exactly 2,304 training tokens. Pause. What does the fit look like? Pure linear algebra. No learning theory needed. As many equations as unknowns, inputs in general position, the system has an exact solution. Training error, 0. Guaranteed. And here's the horror. That stays true if the target is pure random noise with no relationship to the inputs whatsoever. Perfect training fit is not evidence of a relationship. It's evidence you had as many knobs as data points. Now, if you're paying attention, you should object. But we don't have 2,000 tokens. We have 150,000. 65 equations per unknown. Massively overdetermined. The horror story doesn't apply, does it? The objection is correct, and it deserves a real answer. Two of them. First, those 150,000 tokens are not independent witnesses. They come from consecutive text. Neighboring tokens carry nearly identical residual vectors. The effective number of independent samples is far smaller than the count. Second, and deeper, the stream's variance is wildly uneven. A few loud directions carry almost everything. Thousands of quiet directions barely move. Along the loud directions, the data pins T down firmly. Along the quiet ones, the data whispers. And least squares, forced to choose something, fills those directions with amplified noise. The fitted map ends up confidently wrong, exactly in the subtle directions where interesting features live. The paper's response has two levers. Lever 1, ridge, penalize large entries of T, so where the data whispers, the fit stays small instead of screaming. The formula arrives in video 3. Lever 2, the central move, constrain the rank. One big square matrix. Force T through a bottleneck. First, compress the 2,000-dimensional vector down to just R numbers. Then expand back up. Two thin matrices. At R equals 64, that's about 300,000 parameters instead of 5.3 million. The map can only express R independent channels of transport, and the data genuinely pins it down. Notice this closes the loop constraint 1 opened. Consuming the whole vector was necessary but dangerous. The bottleneck makes it safe. Constraint 3, control the capacity. And that number R is now a dial. Turn it up and ask, when does prediction stop improving? Remember the dial. It becomes the star of video 4. Last trap, the sneakiest, because it bites after you've done everything else right. You fit a capacity-controlled map. Now you score it. Aggregate R squared across all 2,300 coordinates at once. It comes back 99%. Champagne? Pause. What can a 99% aggregate hide? Two coordinates expose it. Give coordinate 1 variance 100, a loud, boring bookkeeping direction. Positional information is the classic example. Give coordinate 2, where your feature lives, variance 1. A lazy predictor nails the loud coordinate and predicts a constant for the quiet one. Total squared error 1, total variance 101. Aggregate R squared 99%. Score on the coordinate you actually care about, error 1, variance 1, 0. Total failure on the feature, invisible in the aggregate. The loud direction paid for the quiet one's sins. The fix is to evaluate through the keyhole, and this is literally equation 1 of the paper. Project the true downstream vector onto df, the true reading. Project the predicted vector onto the same df, the predicted reading. Compare them with R squared, feature by feature. And here a doubt from video 1 should resurface. Hold on. In the SAE, activations came from an encoder with its own weights and a ReLU. Is the true reading the encoder's output? No, and the distinction matters. The paper score uses the plain dot product with the decoder direction, exactly as written. The encoder plays a different role. It decides which features are active, where to point the keyhole. Once a feature is chosen, everything is measured with the decoder ruler. Division of labor. Encoder selects, decoder measures. Constraint 4, score in feature space. And now, a small payoff. This is the actual paper. Equation 1 exactly as printed. True projection, predicted projection, compared with regression metrics. Every symbol on that line is now yours. Look at what the wreckage bought us. 1. The test must consume the entire upstream vector. Tracking a single coordinate is meaningless under mixing. 2. Regression and ablation answer different questions, form versus reality, so the method needs both. 3. The map must be capacity controlled, a rank bottleneck plus ridge, otherwise it fits anything, especially in the quiet directions. 4. The score is taken through the feature's own keyhole, not on the raw vector. One honest wrinkle to carry with you. The map is fitted on the whole vector, but judged per feature, so a low score could mean synthesized, or that the bottleneck spent its budget elsewhere. Keep that suspicion. Video 4 builds the tool that settles it. Now, pause for real. Write the method. What do you fit on what data, and what number do you report? There is essentially one design left standing, and you hold every piece. Whatever you wrote, compare it against this, the paper's own methodology, straight from page 2. A rank-constrained, ridge-regularized affine map from upstream to downstream residuals, scored per feature through SAE decoder projections, and causally validated by ablate and inject. You can read most of that paragraph cold, and next video we build every piece of it with real formulas. Homework. 1. Derive the least square slope. Write the average squared error of a line, differentiate with respect to the slope, set it to 0. The covariance over variance formula we use today will fall out. 2. Verify by integration that the average of z cubed is 0 for z uniform between -1 and 1. 3. The 2x2 version of the square system trap. 2 equations, 2 unknowns, random targets, show the exact fit. 4. Write your 1-paragraph method proposal. See you in video 3.